Exponential decay mathematical model is commonly used in environmental science because the rate of transformation of an entity in nature is often primarily controlled by the abundance of that entity. These mathematics are commonly used for phenomena like first-order chemical kinetics, radioactive decay, organic matter decomposition, depletion of storage in a linear reservoir, among many others. Another real-world example is continuously compounding interest, and the exponential derivations are very similar with the exception of exponential growth having a positive exponent rather than the negative exponent used in exponential decay. We're going to review exponential decay in the context of first-order chemical kinetics, but you will see the same basic derivations applied over and over again in applications across environmental science. The idea of first-order kinetics is that the rate of the consumption of a chemical reactant will often be linearly related to the concentration of the reactant. This comes from the idea that the concentration of the reactant is a direct control on the probability that a given molecule of the chemical will encounter another reactive component of the system. The mathematics of first-order kinetics are usually first expressed as an ordinary differential equation. This notation allows us to think about the controls on the rate of change in something over time, which is usually more intuitive to link with theory than thinking about the controls on the absolute magnitude of something. In the case of first-order kinetics, we are saying that dc/dt, or the decrease in concentration of a reactant over time, is linearly related to the concentration of the reactant. In this case, the proportionality constant is this Kr variable. Let's do some dimensional analysis to understand this equation and the Kr variable better. For differential equations, the d's are irrelevant to the dimensional analysis. We can treat that first dc/dt term like any other fraction. We can work with any concentration dimensions we want, but in my field, either mass concentrations or molarity are most common. Let's stick with mass per volume as the dimensions of the change in concentration. Because we are talking about the change in concentration over time, then the term on the left side of the equation will have the dimensions of concentration per time or mass per volume per time. We don't know the dimensions of this Kr variable yet, but let's figure it out based on consistency. Again, we have dimensions of concentration on the right side of this equation with the Kr. This is a dimensionally consistent equation because it turns out Kr has a physical interpretation other than just being a proportionality constant. Can you figure out what the dimensions of Kr must be for this equation to be dimensionally consistent? You may want to pause the video and think for a minute and see if you can figure it out. It turns out that Kr has to have dimensions of per time. This may seem illogical at first, but you might also think of it as a ratio of concentrations per time, where the dimensions of the ratio of concentration divides out to unity. In other words, Kr is like a continuous interest rate, in that it is a fraction or percent of the concentration of the reactant that is being consumed per unit time by the reaction. Kr is typically called either the first-order rate constant or the first-order rate coefficient. The differential equation is useful for describing the theory, but not very useful for calculating numbers. What we really need to do is solve this equation for concentration, so we have some way of using this math to predict concentration as a function of time. The first step doesn't even require calculus. It is the same thing you do for any algebraic solution. We need to get the terms with the variable we are solving for on the left side of the equation. In other words, we need to divide both sides of this equation by c and multiply both sides by dt to get this result. Now the calculus kicks in, and we recognize that getting rid of the d's requires some integration. We might also recognize that minus Kr is a constant with respect to time and can be pulled out of the integral on the right side of this equation. To solve those integrals, we need to know the antiderivative of the formula within the integral. The antiderivative of 1 over c times dt is the natural log of c. The antiderivative of dt, or 1 times dt, is just t. One more bit of calculus here is to recognize that differential equations only describe how the value of a variable is changing and have lost information about the absolute magnitude of the variable. Therefore, anytime we integrate a differential, we have to add a constant of integration to recognize the effect of that lost information. Both integrals here have constants of integration, but these are both just numbers, so we can add them together and call them whatever we please. Let's call the sum of our constants of integration y. We can figure out what the constant of integration represents by calculating its value at a particular time and at the concentration occurring at that time. In this case, it turns out to be convenient to think about the concentration at time 0, which we will call C0. Substituting 0 for t eliminates the kr term, and we quickly recognize that y is equivalent to the log of the concentration at time 0, which we might also call the log of the initial concentration. Now we can plug the log of the initial concentration in for y and derive an explicit formulation for predicting c as a function of time. If we take both sides as an exponent of Euler's number, we can get rid of the natural logs. The natural log of c goes away immediately, but we need to apply the addition rule of exponents before we can get rid of the natural log on the C0 on the right side of the equation. Ultimately, we arrive at the well-known and widely applied exponential decay equation. I'll leave it to you to check our derivations by confirming this equation is still dimensionally consistent.